Let's take a look at some properties of this new logarithmic function. So remember, the inverse of an exponential function is a logarithmic function. That means that the inverse of a logarithmic function is an exponential function. Okay, so the domain, the properties of logarithmic functions, one of the most important ones is that the domain is not all real numbers. Right? So the domain of a linear function is all real numbers. The domain of a quadratic is all real numbers. The domain of a polynomial function is all real numbers. The domain of an exponential function is all real numbers. So we had other rules about restricted domains. So one rule we said was that you can't have negatives underneath a square root. You can have 0 and you can have positive numbers under square root, but the square root restricted us. Also, when we divided by numbers, or divided by x's that could be equal to 0, those also were issues with the domain. So with rational functions, we didn't have all real numbers because we could have been dividing by things that made the denominator equal 0. So the logarithmic function is the last type of restriction that we want to look at. So the rule for the domain for the logarithmic function is the inside of a log must always be greater than 0. So whatever's on the inside of the log must always be larger than 0. It can't equal 0, it has to be larger than 0. So if we look at this example, f of x equals log base 2 of x minus 7. We're saying the inside of the log, x minus 7, this has to be larger than 0. So we are trying to solve x minus 7 is larger than 0. Inequalities, hopefully you're comfortable with this. You add 7, so we're saying x is larger than 7. And remember, domains we usually write in interval notation. So we're saying x is larger than 7, so this goes from 7 to infinity. So this is the domain wherever the inside is larger than 0. But we can make sense of this. Why is this the restriction? Why is this even the domain if we think about our graph transformations? So if we just have regular log base 2 of x, we have this general function here. The domain of this function is going to be 0 to infinity. This was the type that we looked at in the last video. The inside must be larger than 0, so x is larger than 0. But when we have a minus 7 on the inside, if we think about graph transformations, this is going to be a horizontal shift, 7 units. And because it's a minus 7, we're shifting that 7 units to the right. So we now want to shift over 7 units to the right. And this is now our function. And so this would be over here at 7. So this over here at 0 got shifted over to the right 7 units. And this says that all numbers from 7 to infinity are okay as long as we're not including 7. So we can see this rule based off of graph transformations. So another property that we want to be familiar with is how to go between logs and exponents. I'm going to ask you lots of questions. This ability will help us connect these two worlds of exponents and logs, is to be able to rewrite an exponent as a log and a log as an exponent. So how you can remember it is, so the way I remember it is I have b raised to the exponent equals some number. So the base to an exponent is some number. If I want to write that, that's my regular style of an exponent. If I want to write that in logs, I will instead write log base b of n is equal to the exponent. So the way that I was taught to remember this is pretend you're a southerner and you're saying log b an exponent. So log b n exponent is how we want to do this. Now when we write this, b is the base. It's going to be written below. N is going to be normally in parentheses. That's going to be the inside. That's like the stomach of the log. That's what's really inside of the function. And then on the other side of the equal sign is the exponent. So we see an example of how this works for 3 to the x equals 9. What this would be in logarithmic form is I have my log, my base over here is the base over there. So the base is the same in both of these. So I have a log base 3. Then on the inside of the log is going to be this n. That's on the other side. So that's going to be 9. And this is equal to the exponent equal to x. So log base 3 of 9 equals x. So that's how we go from exponents to logs. Go in the opposite direction, so I have log base z of x plus 2 equals 4y. So now we start throwing in some variables here, a lot of them. We just follow this property, right? If I want to write an exponential form, I have to find my base. My base is the same. My base is z. The exponent of my exponential function is on the other side of the equal sign. So that's going to be to the 4y. And then this is equal to some number. This number over here was the number that's on the inside. So this is equal to x plus 2. So this is now this in exponential form. So these two are equivalent to one another, whether or not you're writing them in logs or you're writing them in exponential form. So then using these properties, we could solve some of these types of exponential expressions. So I could evaluate this. Log base 5 of 25. We'd like to figure out what is this equal to. Now, if we can't, normally we can't think about logs. You don't have enough intuition. I don't even have enough intuition to think about these strictly as logs. I have a lot of intuition with exponential functions, so let's try to use that. So if we want to do that, if I want to try to write my log in exponential form, I need something on the other side of the equals. Well, there is no equal sign, but I could say this is going to be equal to x. So I introduce an equals to x, and now I'm going to change this into exponential form. So using this property back and forth, I have 5 raised to the x is equal to 25. So 5 raised to the x is equal to 25. Now, this statement, hopefully you can now think about, what is x? Right? What power do I raise 5 to get 25? Well, you should come up with x is equal to 2. So that is my answer. Log base 5 of 25 is 2. Doing this over here for log base 7 of 1/7, again, I set this equal to x, then I turn this into exponential form. So I have 7 to the x is equal to 1/7. Now, if I have 7 raised to what power gives me 1/7, well, somehow 7 has to go to the bottom of the fraction. And as we talked about a little while ago, we said that negative exponents do that for us. So if I raise this to the negative first, it works. So x is equal to -1. And so these are some of the properties of logs. There's going to be a few more that we would like to learn and be able to continue to relate these two ideas of logs with exponents.